And the third one is a right triangle. The right triangle is very special. The also the circumcenter is the midpoint of this side because we proved the theorem. This is half of the opportunity side. So this point has equal distance to all three vertices. So this is the circumcenter. On the other hand, because this is a right angle, so this is perpendicular altitude, the two altitude intersect that also center. So for the right triangle, the also center, the circumcenter and the also center, they are very special. One is on the side, one is the vertex. Okay, so this is about the homework. So we will start today's lecture. Last time we introduced the coordinate system. We use this R for all real numbers. Now for the plane, we have a pair of real numbers, X, Y. So we use R square. We say R square, but it actually means the plane, two-dimensional plane. We have the following. This will be our x-axis, y-axis, origin, and units. The two axes divide the plane into four quadrants. The first quadrant, where both coordinates x and y are positive. Second quadrant, this is the first, second, third, fourth. So I use this Roman letter instead of the the Arabic numbers. It's convention to use this 1, 4, 1, 2, 3. Second quadrant, x is negative, y is positive. Maybe yes, maybe you. Third quadrant, both are negative. And the fourth quadrant, so when we see quadrants, usually we do not consider the axis. Points on the axis are not in any of the quadrants. Then we will draw the circle. We draw a very special circle. It's a geometry class. We know how to draw circles. We draw one of them. This circle center at the origin. And radius 1. So make this 1. Okay. All right. Yeah. We consider this very special circle. We call it the unit circle. Okay. So unit, so referring to the radius is 1. Call it the unit circle because there are a lot of different unit circles. This one corresponds to the one with center at the origin. The unit circle. Okay. Next, we will pick a point. Okay. Now let's check what's the distance between this point and the origin. Okay, I have one answer over there from Amy. Yes. Jessica, what's the distance from a point on the circle to the origin?
The radius?
The radius is 1, the
Oh,
distance
1.
is 1.
Yeah.
What's the formula for the distance? So OP. Let's if we connect this, we have this is 1. To find a formula for this, I'm going to draw a perpendicular line. Okay, now let's check. If the coordinates are x and y, what is this size? Kira, any guesses?
Um, half of 1?
Well, so this point, x and y, what does this mean?
The coordinates?
The coordinates. So it means this will be the x coordinate.
So that distance would be like 0 to x.
So this will be x. What about this?
Y.
y. Aaron, now we know x and y. What's this side in terms of x and y?
That is x squared plus y squared equals 1.
Okay, so this means
But that's still 1 because root 1 is still 1.
equals 1. So now we get equation for the unit circle. We say this is the equation for the unit circle. It means for any point on this circle, the coordinates x and y satisfy this equation. On the other hand, for any x and y, the corresponding point is on the unit circle. So two ways. One, any point. This is the equation. Two, if x y satisfy the equation, okay, two-way implication. If it's on the circle, then x and y satisfy the equation. If x and y satisfy the equation, then this point that's on the circle. That's why we call it the equation for the unit circle. Okay. Next, we will introduce the position angle. Any point, we will connect P to the origin. The angle from the positive x-axis is denoted as theta. Is called the position angle. Again, we will draw the unit circle. We pick a point. And we measure the position angle. Okay, so we pick a point. Two requirements. First is in the first quadrant. Also on the unit circle. Now we want to find a formula for the two coordinates in terms of the position angle. Okay, let's think about this. Could you give me a formula for the two coordinates of this point using this angle? Amy, Aaron,
You like
yes.
make it a right triangle again,
Okay, let's make the right triangle again.
and then so that side divided, wait, and then if you somehow manage to find the lengths, I don't know.
Okay, that's a good observation. Let's try to find the length step by step. Okay, first, what's this side? What's the length of this side? The hypotenuse, Amy. Okay, you are muted, but I guess you said 1. We know this is x, this is y. Okay, let's try to recall the trigonometric functions. Aaron, what are the trigonometric functions? Okay, Aaron is eating. Kira, what about you? Okay.
I was gonna say x squared plus y squared equals 1.
We already have that one. Now we want to use the angle information, theta.
Sine and cosine.
Okay, which one is the sine?
Sine is let's see now, in this case, it'll be y over x.
Okay, Kira, you disagree.
Wouldn't sine, since sine is like the opposite side, so wouldn't that just be y?
Okay, so it should be y over 1, just y. So we should have sine theta. Okay, Jessica, what about x?
Um, cos.
What's okay? So
Oh
in
no.
this triangle, cosine will be x over 1. Is x. What Aaron said, y over x. Aaron, what's this? Y over x,
Sine over cosine.
which is
Tangent.
nice, nice.
I thought you said tangent, so I said
Okay, maybe. Okay, okay. So now we have x and y. We can substitute x and y in this equation by the functions theta. So equivalent equation. Let's just say from the equation we have. The identity. So x is cosine. The cosine square. Again, I will put a square on the root of cosine, which is 1. So we have a formula. Very useful formula. Previously, the two functions, cosine and sine, kind of irrelevant. They satisfy this identity. And we verified this before for some special angles. Okay. Now we can allow the angle to move. Previously, we only consider the point in the first quadrant. If we move to the second quadrant, we have the same equation.
isn't it negative x?
Okay, give me a second. It is. Origin 1, 1, y, x, y. Okay. First, what can we see about the position angle? For points in the first quadrant, the angle will be between 0 and 90 degrees. What about the points in the second quadrant? What are the ranges for such theta? Aaron,
Let's see now. What's the second quadrant?
in the first quadrant, this is 0 to 90 degrees. 0 to 90. What about one over there?
It's greater than 90.
Greater than 90 and
Hmm?
what's the upper bound?
Less than 120?
Okay, almost 180.
Oh, wait, yeah.
Okay, second quadrant. For these points, we still find x and y. We still have these formulas. We can use this to define sine and cosine. We still have x and y. So cosine theta will be x. Let's compare the two equations. They're the same equations, but they represent different meanings. This one, we found x and y, we compute, we verify x is cosine, y is sine. For this one, we can find x and y. Then we define cosine and sine to be x and y. So this defines in the same way we can consider points in the third quadrant. All points in the fourth quadrant, the same formula holds. So for any point on in the circle, we can define so that theta is the position angle. So when the point moves around the circle, the position angle changes. From here, it's small, larger, and larger. Angle changes, the x and y coordinate changes. This specifies the function. In this way, we can define cosine and sine for theta from 0 to the whole angle. What's the whole angle?
360.
360. So this is defined for
Isn't that? Oh, wait, what is it? The fourth quadrant?
that also applies to this formula. This formula applies to first, second, third, fourth, to any point on the circle.
Mm-hmm.
It includes, yes.
What about the third one?
For the third one, we still have this. So if point is in the third quadrant, it means cosine is negative, sine is also negative. Both are negative.
Yeah, but for the angle, what's the constraint?
Okay, so let me label this. We start at 0, and then use a different color. 0 and over there, 90, there, 180. Okay, Aaron, what's this one?
270?
Yes, 270. Then we go back to 360. Okay, so we use angles, but in mathematics, very often we use a different measurement called the radian. It's a different measurement. A complete revolution of it in a circle. We have two ways to see this. Use degrees. If we say degrees, we know it's 360 degrees. We can also use the circumference of the circle. Okay, it's a good time to recall what's the circumference of a circle with radius 1. Jessica,
Wait, what was the question?
what's the circumference of a circle with radius 1?
Um, 2 pi.
Okay, so this will be 2 pi. Okay, so this will be the radian, 2 pi radian. This equal to 360 degrees. Okay, now I'm going to give you some questions. If I have pi, what's the corresponding degrees? If I have 90 degrees, 270 degrees, 145, and 35. Okay, I'll do it one by one. Amy, I have radian pi. What's the corresponding degrees? Pi 360. Pi is
180.
180 degrees. Aaron, now I have 90 degrees. What's the corresponding radian?
Let me see. Half a radian.
Pi over 2. Kira, 270.
1.5 times pi.
Okay, so sometimes we say 3 pi over 2. Jessica,
Wait, pi over, wait,
this is half of 270, right?
so, 3 pi over 4.
Mm-hmm. Okay, now the interesting question is, what is 1 radian? How many degrees? $60? $90? Okay, Kira.
So if wait, hang on. 2 pi radians equals 360 pi. Does the pi also have a radian?
Pi radian is 180.
180. Wait, never mind.
Okay, 1 radian. You okay? That's very close, Kira. Almost there.
I
It's
feel
like
like it's 1. I don't know.
it's like 180 over pi. Is that right?
Okay, yes. Okay, so that's what
That's like
I want to tell Kira. So
it's,
pi radian is 180. We divide both by pi,
it's somewhere below 60. I know that.
we get it. Okay, so this is
180 divided by 3.14159 something.
okay. What pi is? Okay, that's a different question. At least now we know what is 1 radian. It's a little bit strange. It's not this is not integer. Okay, so be aware of this. When we see radian, if you see 1 radian, it's corresponding to a very special angle. Okay, what is this angle? How do you draw this? Okay, so the point is the radian and the angle, they correspond to the same arc of unit circle. That's the connection between them. For any arc, let me draw an arc. We have two measurements for the arc. One is the corresponding angle. Two, let me finish this. We can measure the length of this arc. The length will be the radian. In particular, this one radian corresponds to the arc of length 1. If the length is 1, then this angle is what we're looking for. If you can find a piece of the circle with length 1, the corresponding radian will be 1. Okay, so we'll pause here, stop for 5 minutes, and we'll be back at 10:21.
Thank you.
Okay. So now we have two systems. One is the degrees, one is the radians. Okay. And previously, we are using the degrees all the time. But in the future, we will rely more and more on the radians, because the radians, they are referring to the length. It's more measurable. The degrees is kind of arbitrary. So, and we have, let's complete the following table. Radian, degree, 0. Let's find the corresponding degrees. If the radian is 0, what's the degree? Jessica and Amy. If the radian is 0, what's corresponding degree?
0?
It's 0. Why?
Because if it's like 0, then the angle is just
Okay.
logical. Yeah,
If the
you can
arc
see.
has 0 length, so the angle is also 0. Okay, it's consistency. Okay, Aaron, pi over 6.
Hold up. Where are we? Oh yeah. Uh, let me think. 60 degrees?
How do you get a 60?
Wait, wait, no. Forget it. What's it called?
So the hint is over there.
Yeah, I need that. 30 degrees, I think.
Okay. 30. How do you get a 30?
Because if you do it to 3/2,
Mhm.
and then multiply by 3 and then divide by 3. I mean, yeah.
Okay, so one way is we can check pi is 180. We divide by 6. Divide by 6 get a 30.
Uh-huh.
Okay, Kira, pi over 4.
45.
45. Jessica, pi over 3.
Wait. 15 degrees? Wait, no, I mean, 60 degrees?
60 degrees. Okay, Amy again, pi over 2.
75.
How do you get a
I don't know, I'm
75?
just, huh?
How do you get 75?
I'm following the pattern.
Use mathematics, not the pattern. Okay, it's over there.
90.
Mm,
Technically, patterns are also mathematical.
okay, sometimes it is. Because you see, the pattern here is different. It's not the same. Pi over 6, here pi over 3. Different pattern. Okay, now let's recall the values of these special angles. Sine. Oh, I went back to sine, cosine. Okay, who wants to start? Sine 0.
It's 0.
Why?
Because if you multiply something by 0, then it's 0.
I didn't get that. What's that?
Like, if you have like a 0 for sign, then that means it's just 0. If you divide,
Okay, okay. Oh, we can use the correspondence. Sine 0 degrees, which is 0. Okay, so Aiden started. Kira next. Sine power 6.
30?
Sine 30 degrees, which is
I think it was 60.
no, it's a very small number.
Oh.
Okay, it's a while ago in our homework. Okay. Jessica,
Zero. Wait, no.
no.
Um, uh,
The fraction.
oh, pi over 6. Wait, no. Wait, I don't know.
Amy, all the homeworks.
Let's see if I remember.
Okay. We used the several theorem. We proved this a while ago. It's 1/2. Okay, Amy, next one, sine power 4. What degree?
45.
Which is, remember this one?
No.
Okay, so this one is very special. If one give a right triangle.
I think I'm out. I think I know. I think
Is
Okay,
it?
okay, okay.
bold guess, but root 2/2.
Amy, is that your answer?
No, I was gonna say something like that.
Okay, so it will be root 2/2.
I
Okay,
remembered
Aaron.
it as 2 over root 2, but I think it's root 2 over 2.
Okay. Aaron, power 3,
That's sine 60.
which is
Uh, uh, root
okay.
2, perhaps. Oh, was that right? Was that right?
What's the answer?
Root 3?
Okay,
Wait, was that right?
okay, yes, that's right.
Cool.
Sine 90 degrees. Kira, do you remember this one? Sine 90 degrees.
1?
Yes. Okay, Jessica, we're back to cosine 0.
Hmm.
Uh, oh, sine, cos 0 degrees.
Cosine 0 degrees, which is
0.
no, sine 0 is 0. What about cosine 0?
I don't know. I forgot.
Mm-hmm. There's a relationship between sine and cosine. What's the relationship? The about complementary angles. So we can apply the complement angle formula. Cosine 0 now becomes sine 90 degrees, which is 1. Okay, Amy, next one. Cosine power 6.
Uh,
Step by step. What degree?
60.
Well, could will be, but the first step, pi over 6, 30 degrees.
Oh, right.
Then we apply the complementary angles formula, sine 60 degrees. Then we look up our result, it's over there. Okay, Aaron, cosine pi over 4.
Cosine 34. I mean 45.
Which is sine
5. That's root 2 over 2.
Kira, cosine pi over 3.
Is cosine 60, which is 1/2. Well, sine of 30.
Jessica, cosine pi over 2.
90.
Which is sine
0.
0 degrees. This is 0. Okay,
Yeah.
so we used our knowledge about the sine degrees, cosine degrees. We find sine and cosine for the radians. Okay. Now, let's have a rough graph of this. So we will use x for the variable. We'll consider the following function. X measured in radians, sine x. Okay, now let's complete the following x and y. X0 pi over 6 pi over 3. I'm sorry, pi over 4 pi over 3 pi over 2. Find the y values. Then mark the points on the coordinate system. This one we can go a little bit further this way. Pi over 2 is about 1/2, a little bit more than 1/2. Pi over numerically, pi is slightly bigger than 3.14. So pi over 2 is approximately 1.57. Pi over 3. Okay, so let's start with Amy. When x is 0, what is y?
Also 0.
0. Aaron, x power of 6.
That's like sine 30, which equals a half.
A half. Kira, power of 4.
Sine of 45. So that's
Which,
square root of 2/2.
Jessica, paper 3.
Square root 3/2.
I'm not sure if Peter got here. Peter? Okay, maybe not. So, Amy, back to sine paper 2.
1.
1. I will give you a few minutes to mark this point, this point, this, with 5 points on the coordinate plane. So where are they?
I use a calculator.
Well, approximately. You don't have to be precise. Okay,
Okay.
first one. This one's easy. What about the first point? 0, 0. Where's this point?
0.
The origin. Okay, we have 1 point here. Okay, second point. X is power 6. Y is 1/2. So a half will be somewhere over there. Next one, power 4. Power 4 because this is bigger than 1/2, smaller than 1. We have slightly bigger. And at 1. The 5 points. We connected them with a smooth curve. So this is the graph of y equals sine x. And part of, because y is sine x, well, x from 0 to pi over 2. Okay,
That big
next.
trigonometry, this thing.
What's that, Aaron?
This topic be called trigonometry.
Uh-huh. Yes.
And that's a function, so a trigonomic function.
Yes.
Okay.
I'm going to make a copy of the points and ask you to draw the cosine function. Mark this 1 pi over 2. Okay, rewrite pi over 3. Again, I will make a table. Y is cosine x, x, and y. Zero. Pi over 6. Pi over 4. Okay, this time I'll start with Jessica. Cosine function. X is 0 is y.
0,
No.
90.
So cosine 0, sine 90, which is 1.
Oh, yeah, 1.
Okay. Amy, cosine power 6.
The 30, I think.
Cosine 30 is sine 60.
Yeah.
Okay. Aaron. Maybe Kira. Power 4. Okay, Aaron here. Okay.
Screen glitch. Root 2 over 2.
2 over 2. Kira, power 3.
1/2.
1/2. And last one is 0. Okay, let's mark the points. X0, y equals 1. First point. I marked the points wrong. Let me make corrections. This should be 3. This should be 6. 3. This point is 1/2. Okay, the 5 points. And I should make some adjustment to this one. And make a corrections a little bit off. So this is 1/2. Okay, I make a mistake. Should be x here, not 0. Okay. So we defined the two functions, sine and cosine, in terms of the measurements, actual numbers instead of degrees. Then we have the graph of this. A very important property of these trigonometric functions is the periodicity. A function is periodic.
What's T?
Okay, so here t for sum makes a new class of functions. It's periodic if you can find a number t such that the values of the function when shifted by t is the same as the initial value. Okay. Let's check if we consider the linear function, something you learned in algebra. Can this be a periodic function? is fx. To check whether this is periodic or not, we will compare the value at x with the value at x plus t. We substitute x by x plus t. And we distribute this with ax, at.
I was gonna say that.
What's that, Aaron?
I was gonna say that same thing.
Okay, plus b. When will this be the same as ax plus b? Amy, you want, huh?
If t is equal to 0.
Okay,
But t is greater than 0.
okay, that's
But it
nice.
says for some.
Okay, so first, let me make cancellations. I cancel this term, so have a simpler formula. When is at 0? Well, for this to be periodic, t must be positive. T is positive. What does this imply?
At is not 0. I mean, a
What?
is not equal 0. Because,
So at is 0. T is positive.
then a is 0.
Then a must be 0. Okay, so now we see, could it be periodic? We say yes, but only when a is 0.
Wait, in that case, couldn't you just say all real numbers or something in that case?
Well, we don't see number. So this will be a constant function.
Oh.
Fx
Okay, let me write
equals b. We call it a constant function. The value doesn't change, so it's a constant function. So for the linear function, for it to be periodic, it must be constant. So it's very rare. But our function here, the sine and the cosine, it turns out to be periodic. The reason for this is that when we define the functions, we use the position angles. Now we see if a point moves around the circle one loop, start at 0, get back to 360. In particular, we know sine and cosine 360 should be the same. So here we can add the unit circle. If we move around this complete circle, then everything starts over. Another circle, we start again. Each time we go around the circle for complete revolution, then we start the process. This implies cosine 2 pi. Okay, don't have to write 0, just the radian. We have the following identity, very important identities.
Does that say reutilization?
Revolution,
Oh, I
okay,
could.
but from revolve means rotate around something. Rotate around this, complete revolution will go around the whole circle.
Okay, yes, but I just gonna read that.
Okay, so now we can conclude the two functions are periodic and 2 pi is a period. So conclusion, sine x and cosine x are periodic, and 2 pi period. Okay. The last few minutes, let me give the complete graph of the sine and the cosine function. Two pi. Because it's periodic, you just extend this over and over again. This is sine x. Okay, so these are the graphs over one period from 0 to 2 pi. Then it's periodic to repeat. Okay.